In this video we're looking at the three different ways of heat transfer, or three different ways that you need to know at this level. So we're interested in this idea of heat transfer because it's energy, heat energy, and physics is all to do with energy. We're talking about how you can transfer energy from one place to another. So first of all, let's look at conduction. Now this relies upon the kinetic theory of matter, where your particles, this might be a bar of metal with a whole bunch of particles inside them, and you apply a flame with some heat to one, and the kinetic theory of matter says that heat is really just kinetic energy of vibrating particles. So what that would do in terms of heating up and transferring energy from this position down to this position is that this first particle would vibrate back and forward and bump into the next one, causing that to vibrate, and while that heat is continuing to transfer energy from the flame particles bumping into the metal particles, the vibrations will just carry all the way down to the far end. So you've successfully transferred your heat energy by vibrating particles, and that's what we call conduction. Okay, another important thing to talk about this is the temperature is different from the thermal energy. Okay, so as far as the concepts, when we're dealing with concepts in a physics sense and not in a layman's sense, the temperature is what we talk about when we talk about the kinetic energy, in fact the average kinetic energy of the particles. So we would look at the total amount of energy and divide it up over the number of particles, and we'd have an average kinetic energy. Okay, we don't need to worry about a quantitative, that is a numbers approach to this. Just as a concept, the particles are vibrating and they vibrate at an average amount, and that's what we call the temperature and the kinetic energy of the particles. However, the thermal energy is what we would deal with the total kinetic energy. Okay, so you add up the kinetic energy for each particle until you get a total. So in this sense, the total kinetic energy will be greater for a larger quantity. So if you've got a piece of metal that is 2 times larger than another piece of metal, okay, and so this might be m and 2m. They're at the same temperature, so the temperature is the same. Therefore, this one that's twice as large has a greater thermal energy because the total of number of particles is greater. So but they both have the same average kinetic energy for their particles. Okay, that's cool. We'll move on to convection. Convection is when you have, there's a lot of examples to try and explain this, but let's talk it like this. Hot air, finish the sentence, starts with R, yes, hot air rises. This is convection. So you have those flow of hot air going up, and then let's start this. We might have a hot plate on a stove top providing heat. The hot air over the top will rise as it takes up more space. This is the same way that a piece of cork will float on water, because the cork is less dense. Okay, so the less dense air, which is hotter because it's the air is expanded because of that extra kinetic energy vibrating the particles to take up more space. That less dense air rises, and you have more dense and cold air coming in from the sides. Okay, and then as this less dense air has to move off to the side to make way for more air coming up, and as that less dense air begins to cool, okay, it begins to sink back down again, and you get these convection kind of cycles going around and around and around and around, and in all sorts of different ways. So that's how heat energy is transferred by convection. And the last one, radiation. This is an exciting one. Radiation is exactly how you would expect. So radiation takes a piece of anything. This could be something radioactive, but it doesn't have to be, and it could be hot, could be glowing hot, and that glowing heat could be copper that's glowing kind of red. Will transfer heat by radiation. So the particles of air are not transferring, although if there was air they could. In fact, let's just set this up even bigger. We'll put this in a vacuum. Okay. Vacuum means there's no air inside there. Because there's no air inside, it means you can't have conduction, because there's nothing touching this glowing hot object. And you can't have convection because there's no air to expand and increase the kinetic energy and then rise and move around. Okay, so but this will cool down over time in the same way that stars will cool down over time. It radiates heat energy in the form of light, not always visible light, but infrared light and UV light. All these photons of light are just radiating off and transferring it, and that way they can go through the vacuum of space from the sun to the earth. Okay, so that's your conduction, convection and radiation. It's good to compare and contrast all of those. Conduction requires that contact between particles. Convection requires that the material can expand and the hot parts can rise, so the energy is used to make it rise. And radiation doesn't require anything, it'll just radiate off the heat. And this is the same way we get sunburnt as well, by the radiation from the heat energy from the sun. Okay, so one little example really quickly just to finish off. If you have double glazing, how does that help reduce heat transfer? Okay, is it by conduction? Is it by convection? Is it by radiation? Which one does it? Well, radiation, the glass is clear, so radiant light energy can pass through the glass. It's the whole point of having a window, so you can see outside. So no, that doesn't help. Convection. Does it prevent particles from rising and rotating? And well, it might stop air from outside coming in, which would be convection current, same as when you open a door and the hot air inside the room rushes out because it's expanded and it's wanting to take up space. So this is a sort of. The main one though is this conduction, because the double glazing is two sheets of glass with either an air gap or a vacuum in between. Same principle as a vacuum flask or a thermos to keep your hot materials hot and your cold. You have a vacuum inside in here to prevent the particles from making contact and touching. Having this air gap is a sort of a cheaper way of doing that, because you'll still get conduction a little bit, but if it's a vacuum, then it'll definitely won't be able to conduct. You have to work out whether it's cost effective in terms of your heating to create a vacuum in the middle, or whether just an air gap will provide enough cost-benefit analysis stuff. Now, you could improve your double glazing and make it harder for radiant energy to get lost if you coat it, and they do this on some buildings, with a very thin amount of some reflective metal. Okay, for example, gold. If you had little gold particles, and they do this on the space shuttle, on the astronauts' visors, you can see that they have that shiny golden visor, which is a heat shield. It stops the radiant heat energy. So if you put your double glazing, you had this glass was infused with gold to keep out as well as to keep in, basically just preserving whatever's in there, it would cause reflection off these surfaces where you've got the gold infused inside of it. So very, very handy. Yeah, shiny things reflect light make for really good radiant energy. Black things absorb and basically attract and heat up from the radiant energy really well, like the hot surface of the road. And white is sort of reflective because it's reflecting all colours. That's why you get the visible full spectrum, which is seen as white. You could reflect it through a prism and disperse all the colours and see what colours are made up of it. But yeah, anyway, gone on long enough. I think we've covered conduction, convection, radiation. There's lots of applications of these. I suggest you try some past exam papers.